Hi everyone, I'm Bhavna Gopal, and today we'll be talking about SAFER, Sharpness Aware Layer Selective Fine-Tuning for enhanced robustness in vision transformers. So let's get to it. We know that deep learning networks have taken the world by storm and in specific vision transformers. So these are widely used in computer vision and multimodal foundation tasks. And you can see a couple of examples of those on the right, such as semantic segmentation or even object detection. Unfortunately, these models are vulnerable to adversarial perturbations, and this impacts both clean and robust accuracy. So, adversarial training is what's been traditionally done to combat this problem. But for ViTs, large parameters and complex architectures actually exacerbate overfitting. Clatt and Rift previous approaches have suggested that layer selective fine tuning offers promise, but a key question is which layers do we actually fine tune? And more importantly, can this be even extended to the vision transformer realm? So, very quickly, some limitations of existing methods for identifying layers suitable for fine tuning. We have higher parameter counts in transformers, lack of inductive biases like weight sharing, and lastly, more diverse layer types like self-attention, which complicate the task of accurately identifying what's critical. So intuitively, you can think that since it's harder to find non-robust layers, it's naturally more prone to overfitting when it comes to models. So SAFER primarily encompasses three different things. It suggests a novel overfitting metric for transformers, which is a sharpness-based method to identify layers prone to overfitting in adversarial training. It then goes and proposes an actual algorithm, which is a SAM-based fine-tuning algorithm. And then lastly, it shows that there is versatile and state-of-the-art performances across the board with different adversarial training strategies and parameter efficient fine-tuning methods. And we see consistent performance gains from about 5% to peaks of about 20%. So let's come to SAM, Sharpness Aware Minimization. So this actually links generalization to the sharpness of the loss landscape. Equation 12 shows that the generalization gap is bounded by how much the training loss increases under small weight perturbations. And equation 13 actually defines the sharpness measure gamma. Sharper landscapes mean more overfitting, and flatter ones mean better generalization. But applying SAM to the whole model is costly. So instead, we ask which layers are the sharpest? So to do this, we define the adversarial loss in equation 14 and extend sharpness to each layer, as you can see in 15. We simplify this using a Taylor expansion, and then we can get a sharpness metric where we can rank all layers with a single backward pass in equation 17. So now that we can actually identify the sharpest layers, how do we actually use that information? And this is exactly what SAFER does. SAFER primarily works in four steps: pre-training, computing sharpness, fine-tuning only the top K sharpest layers with SAM, and then reevaluating these layers periodically. And you can see the updated objective for this in equation 18. The idea is pretty simple. We only fine-tune the layers that matter and we freeze the rest. On the right, actually, you can see that the sharp layers start spiky, but post-SAFER fine-tuning, they flatten out. And now we can actually see how this performs in practice. So in a white box setting, across the board, irrespective of model or data set, SAFER baselines perform better for both PGD and auto attacks. And this was actually seen to be consistent in black box settings as well. We also can see the training curves for different allocations of the PGD pre-training and fine-tuning epochs within a 70 epoch training budget. So irrespective of when we actually begin fine-tuning, we see improved performances. And you can also see the results of starting SAFER from scratch in the purple line. So this could suggest that full model training is beneficial in the early stages for rapid convergence, but layer selective training could help mitigate overfitting and boost performance in later stages. And lastly, but not the least, we look at overhead. So the table here shows the computation times and layers selected at the start of SAFER. And interestingly, layer sharpness ranking actually adds negligible overhead to adversarial training. And it only uses 0.001% of training data every 10 epochs, which just adds overall 0.2% extra time. And how does it actually do this? It turns out that the primary overhead in adversarial training actually comes from computing adversarial examples, which takes multiple back propagations. And lastly, some conclusions. So we introduced a sharpness-based metric to detect overfitting prone layers. We then proposed an actual SAFER algorithm and the four key steps. And then we saw that we achieved consistent gains across models and data sets up to 20%. Our key message being that targeting overfitting layers improves robustness and generalization efficiently in the ViT domain. Thank you very much.